Assalamualaikum warahmatullahi taala wabarakatuh. Selamat pagi. Today we will continue on our lesson for heat and mass transfer subject. Today our topic is steady heat conduction. Steady heat conduction. Okay. Objective today is first to understand the concept of thermal resistance and its limitation and develop thermal resistant network for practical heat conduction problem. This is the first objective of our lesson today. And second is to solve steady conduction problem that involve multi-layer rectangular, cylindrical or spherical geometry. Okay. And the third one is to develop intuitive understanding of thermal contact resistance and its circumstances under which it may be significant. Okay. And the fourth one is to identify application in which insulation may actually increase heat transfer. Then how the insulation improve the heat transfer of one system. Okay, if you add insulation of particular one system, how the heat transfer can be improved as compared to the system that has no insulation. Okay, and the next one is to analyze thin surfaces, assess how efficient and effectively can enhance heat transfer. And the last one is to solve multi-dimensional practical heat conduction problem using conduction shape vectors. Okay, so to simplify our conduction lesson for heat and mass transfer subject, I will not cover on this last two, analysis thin surface, because later on we will go even deeper than that, because this is only surface of what you will know about thin and how to solve in multi-dimensional of the heat transfer. So these two subtopic we will not cover in the conduction, because we have a big topic later on at the course outcome number 3, if I'm not mistaken. Course outcome number 3, we will learn how to design heat exchanger, where we will learn on how to study the thin surface, how to approach the question in multi-dimensional. Okay, so today we will only cover on the conduction of steady state. Okay, conduction of steady state, which is only one direction, 1D, no 2D nor 3D, only one direction. Okay, if I can read for you, the steady heat conduction in plane walls, which is heat transfer through the wall of a house, can be modeled as a steady and one-dimensional. Okay, one-dimensional. What is steady? Steady, which is actually we are referring to something that we analyze, not depend on time, or not the flow itself is not is always constant. Okay, the flow of the heat transfer is always constant, so we call it as a steady. The point is not a functional of time lah, to be easily understood what is steady. And what is one-dimensional? One-dimensional for heat transfer. One-dimensional for heat transfer, it is only one direction. Okay, one direction. For example, I want to study heat transfer in a wall only one direction. For example, I have a wall in my bag here. In one direction, it could be from top to bottom, or from bottom to top, or from the left to right, or from right to the left. That is one direction. Okay, ataupun one dimensional. If the heat transfer in two dimension, what does it mean? Which means if I have a telephone here, I apply heat from the back of my telephone here, then the heat transfer could be to the front or could be to the top or bottom of the telephone. So it is two-dimensional. Okay, if I go even further with three-dimensional, okay, our world, we have only three dimension. We don't have any more than three dimension. So if it three dimension, the heat transfer can go even further. It can through the phone, it can go to me, and it can go to the top and bottom, to me and to you. Macam tu lah. So there are the tiga direction of heat transfer can go. So you can imagine that heat transfer actually transferred in three-dimensional. It's not transferred in one-dimensional. But what we are studying here is only covered on one-dimensional. Be aware with that. So to make it simple, like take a look at this figure 3.1 here. For example, on the, let me change to the pointer first. On this side, for example, on this side we have a higher temperature. Then on the right side here we have the lowest temperature on figures lah. Lowest, of course lah, you can go even deeper, -10, -20, but in the figure here the lowest temperature is 3. Perasan tak yang dia adalah equilibrium? Bukan equilibrium, maksudnya dia evenly, the temperature tu distributed evenly at the surface of the wall. Kalau dia 20 degree di atas, dia pun 20 degree di bawah, dan dia 20 degree di sebelah hujung sana. Same goes with this side of surface wall. Kalau dia 3 degrees at the top and at the bottom 3 degrees, so it is well distributed of temperature. Then the heat rate, we can imagine that the heat transfer from the higher temperature to the lower temperature, right? So it is from the left to the right, from the left to the right. So that is what we call as one-dimensional heat transfer in a plane walls. Okay, ni dekat plane walls. So to study this, we can develop some formulation here. Q in minus Q out equal to dE over dt. Okay, since we are studying a steady state operation, dE over dt can be as equal to 0. So we delete it out in this equation. Then Q in, if we rearrange this equation back, Q in equal to Q out. Okay, so it is simple. So we know that any heat transfer from here, heat transfer rate from the hottest part, it is equal to heat transfer at the outer part on the other side. Okay, since we are studying only in steady state operation, which is no time involved. Okay, Q in equal to Q out. We know that Q equal to, for conduction, equal to Ka times dt over dx. Don't scared with dt over dx. Dt over dx here is referring to the changes of thickness of the wall. Kalau wall tu tebal wall tu ataupun heat tu transfer through the wall, so dia punya change of thickness tu ialah from left to right lah, dan dia punya dx dia adalah ketebalan dia. Kalau from top to bottom, then dia punya dx dia adalah length of ataupun height of the wall lah. You jangan ingat dia hanya transfer from left to right, right to left. Untuk one dimensional ni dia boleh pergi juga from bottom to top, then from top to bottom. It can be like that too. Ataupun from rear to front, ataupun from front to rear. Itu one dimensional juga. So don't scared with dt over dx here, because this dt over dx can be simplified if we put some boundary, where the boundary of the t itself as a surface of the wall. Then we can expand the actual equation here using integral equation. Then we can finally have the Q conduction for wall equal to K times A. A is the surface area of your wall. For example, if you look at the figure here, surface area of the wall is there. We look at the air here, the A, letter A here, and T1 is the temperature of the other on the hottest surface on the other side, and the T2 is the coolest surface on the other side. Then the L is referring to the thickness of the wall. Okay, it is simple as that. So the formulation that you really need to memorize is only this one. Not memorize, you familiarize. Kalau I said memorize, you need to memory, right? But in my cases, you don't have to memorize any equation, because I'm allowing you to bring any equation during test and examination. So at least familiarize with the formula, because we have a lot of formula later on. For this subject, you only interact with the formula. You cannot memorize all the formula. Bear with me, because heat and transfer is the formula is the formula subject. You will deal a lot of formula, and you will need to know how the formula of one particular formula works. So you must be familiarized with each of the formula. But for conduction of flat surface, this is the basic equation you need to know, you need to familiarize, or even you need to memorize it if you want to know more better. Okay, this is the basic Q conduction of a flat wall. Okay, then to make it easier for us for analysis, we always introduce thermal resistance concept to the equation of heat transfer. Okay, we always introduce ataupun simplify this equation using thermal resistance concept. What is thermal resistance concept? If you look at figure here, where T1 and T2 is the temperature, and Q is the heat, and the R is the resistance. So from the basic formula here, you know that R is not there, resistance is not there. but Ka and L can be an R. So Ka and L can be an R. So how to simplify that equation to the thermal resistance concept? We divide this equation to the Ka. Divide this Ka to Ka, and also divide this on the right hand side with Ka. So you can simplify the first equation here to the second equation, where Q conduction of wall equal to T1 temperature higher minus T2 temperature lower divided by R wall ataupun resistant wall. What is actually a resistant wall? If you simplify, just like I said to you, here we divide by K and A, so the R itself is actually L, the length or the thickness of the wall, or the length ataupun the height of the wall ataupun the width of the wall, divided by K, the constant of conduction, heat, and the A is the surface of the wall. Okay, why we call it as a thermal resistant concept? Because it is actually adoption of electrical current concept. Okay, imagine that V1 here is equivalent to T1 there, and the T2 here equivalent to V2 there. While for electric current here, we are studying the current itself, but for heat flow, we are studying the heat rate there. So almost similar concept we applying there. Okay, got it there for Q conduction. Then how about thermal resistance concept for convection? This is for conduction. Conduction, remember from our first lesson, conduction is the heat transfer from solid material. So can we apply thermal resistance for convection? Let's go to the next slide. For the next slide, we know that convection formula, which is Q convection equal to H times AS referring to surface area, then times TS, temperature of the hot surface, tolak, minus temperature infinity. Temperature infinity here referring to temperature environment. Okay, so if we simplify this equation to use thermal resistance concept, then we need to divide the right hand side of this formula with H and AS. So we can simplify the main ataupun the original equation of heat convection to this one, where R convection equal to 1 divided by H times surface area. So in illustration of convection, how they work in thermal resistance concept, this is solid, where your surface temperature is much higher than environment temperature. So if you put it in the table, for example, this is actually your telephone, you put it in the flat ataupun vertical macam ni, you put it in vertical the table, you put it on the table, you punya telefon tu panas sedikit daripada environment, so dia akan berlaku convection, heat transfer from higher temperature surface to the environment which is more cooler surface ataupun more cooler environment. So there is convection core. So in the thermal resistance concept, where Ts there, temperature surface akan release heat to the environment, where R convection, which is actually there, 1 over H times surface area. Okay, read there. When the convection heat transfer coefficient is very large, where H equal to almost infinity, the convection resistance becomes 0, where Ts equal to T. Okay, there is the surface no resistance to convection, thus it does not slow down the heat transfer process. This situation is approached in practice at surface where boiling and condensation occur. We're done with the convection thermal resistance concept. So you may wonder, can thermal resistance concept apply to radiation? Because you know, in the first lecture, you know that heat transfer can be transmitted ataupun can be transferred in 3 modes, which is first mode is conduction, second mode is convection, and the third mode is radiation. So what it is in your mind right now is, does thermal resistance concept can be applied to the heat transfer of radiation? Yes. To answer that is yes. Let's take a look at this next slide, where this is the original formula of heat transfer for radiation, where you have emissivity times Steven Boltzmann times surface area, then times surface temperature power of 4 minus surrounding temperature power of 4. If we want to simplify in thermal resistance concept, we need to remove emissivity, we need to simplify it with the constant number. So we need to make it emissivity, Steven Boltzmann, surface area, kemudian surface temperature and surrounding temperature into resistant radiation here. So if we simplify those here, the R rad can become like this, 1 over H rad times AS. So what is actually H rad here? This whole lot. Okay, this whole lot. So we remember that if you put Q radiation, there must be Q convection involved. Okay, heat transfer for radiation is not working alone. It must be involvement of convection there. For example, if I put my telephone, asyik telefon ni example saya. Example saya ada kuali, ini contoh kuali. Saya letakkan dia di tengah panas. Tengah panas kat luar lah. Dan kuali saya tu lagi panas daripada temperature surrounding kat luar tu. So dia akan berlaku heat transfer. So apa heat transfer yang berlaku, apa jenis mode yang berlaku untuk heat transfer bila saya letakkan kuali yang panas di luar? Yang berlakunya ialah Q radiation dan Q convection. Dia tak berlaku hanya Q radiation saja, dia akan berlaku Q convection juga. So in case of Q radiation, you must know that you must add up Q radiation plus Q convection to get the actual Q total of heat transfer of convection and radiation. You cannot have one radiation alone of heat transfer. Okay, but convection can be alone without a radiation. Radiation cannot be alone without convection, but convection heat transfer can be alone without presenting ataupun present of radiation in the system. Okay, so why we ataupun why engineer love to simplify all this concept to the resistant thermal resistant concept? Why engineer love ataupun want to simplify thermal resist concept of conduction, convection, and radiation? Why? Because it is easier to analyze in resistance, because you can imagine that, for example, we have telephone here. Kita nampak dia macam ada cover dengan telefon lah, but basically inside telephone you have a lot of layer, ada banyak sangat layer dalam dia. So to simplify those layers, it is easier to study heat transfer in one dimensional and using thermal resistant concept. We call it as thermal resistant network, just like here you see in slide there. For example, here we have a wall there. This is your wall, dinding dekat rumah awak tu. Kemudian temperature di luar panas kan, temperature dekat dalam sejuk sikit. Where temperature panas yang kat luar tu kita letak dia T infinity 1. Okay, kemudian T1 ialah dinding luar rumah awak. Panas sedikit lah sebab ada cahaya matahari dan dia berlaku radiation sikit. So temperature yang surface wall dekat luar tu panas sedikit. Kemudian ini ada wall awak, dinding awak. Kemudian T2 here referring to your temperature inside your room. Temperature wall dekat dalam rumah awak. T2 dia rendah sikit lah sebab awak buka air conditioner ataupun you buka kipas. Dan udara di sekeliling tu T infinity 2. Okay, untuk study heat transfer yang berlaku dekat dinding rumah awak tu, you simply can use this formula, which is combination of all those yang you dah tahu tadi. Tu sebenarnya dia bukan benda yang baru pun, dia hanya combination of those resistant concept. So Q equal to T infinity 1 ataupun T higher minus T infinity 2 ataupun T lowest divide by R total. So what is the R total? R total, what happened to the wall kalau berlaku heat transfer? Ada convection, ada conduction. R wall kat sini ialah conduction lah. Kemudian dia berlaku convection lagi sekali. So in basic wall hanya wall saja, at least ada 3 mode of heat transfer berlaku. Convection di luar rumah, conduction dekat kita punya dinding, dan another convection dekat dalam rumah. So to total up that R convection and R wall, then R convection 2, we can just edit all of them, then we can get R total, just like below there here. Okay, R total. You must know lah, R convection is the formula is 1 over H1 divided by A plus L divided by K times A. So this is conduction, this is convection, this is convection. Right? Why we call it as a thermal resistant network? Because it is similar analysis to your electrical analogy here. Similar electrical analogy. Kan? Kalau you ada series of resistor, you nak cari current, what do? You do like this. Resistance you totalkan semua, kemudian you dividekan voltage different, dan you boleh dapat current kat sini kan. Samalah macam thermal resistant network ni, you totalkan resistance of wall tu dengan resistance of convection sebelah luar dan sebelah dalam. You totalkan up dia, kemudian you cari temperature different max and lowest, then you dividekan dia. Barulah you boleh dapat Q ataupun heat transfer rate di sini. So what happened before that? What happened if the question asks you the temperature drop? Temperature drop basically, kalau kita lihat formula ni macam formula yang baru kan, delta T equal to Q times R. Basically this temperature drop formula is derived from this here. This is delta T. R total ni naikkan atas, samalah dia boleh jadi macam ni juga. So the question kalau asking you temperature drop, which is delta T lah, so you ada Q dot, you ada resistance, you timeskan dia, you dapatlah temperature drop. Okay, temperature drop tu ialah difference of temperature. So if question asks you what is the temperature drop of outer ataupun temperature environment di luar dengan surface temperature dekat luar, apakah temperature drop dia kalau you ada Q dan you ada R? So simply Q10 here times 2 lah sini, you boleh dapat 20 degrees Celsius without knowing the environment temperature and also T1 temperature here. Without knowing those, you can simply find the temperature drop if you have resistance and heat transfer rate for one particular situation. Okay. What happen if you have multiple layer of wall? Can you find temperature drop? Yes. Can you use resistant thermal concept ataupun resistant thermal network? Yes. It must dia lebih easier, much more easier than you can imagine kalau you nak kira menggunakan full equation tadi. Okay, sebab you kena tambahkan Q tu baru you dapat full total Q. Kalau you gunakan thermal resistant concept, you hanya tambahkan R saja, you dapatkan maximum temperature dan you dapatkan lowest temperature, you boleh dapat Q. Okay, for example like this. Here we have two walls where dia betul-betul sandwich together, tiada gap di tengah-tengah. Kemudian ada highest temperature there dekat luar dan lowest temperature dekat dalam. I always imagine that highest temperature tu dekat luar lah, sebab kalau di Malaysia highest temperature memang dekat luar kan. Kalau you duduk dekat Korea, lowest temperature tu dekat luar kan. It depends on situation kalau you nak memahami one concept. Then the T1 there, it is outside temperature, surface temperature of the wall dekat outside sekali, dan T2 dia punya middle temperature of the wall, dan T3 inner temperature of wall. Imagine lah, you nampak kan, this is the cross sectional area of wall. So can you find the Q rate? Easy. If you have ataupun you been supplying with R convection, R wall conduction untuk wall 1, R wall conduction untuk wall 2, dan R convection untuk environment di sebelah sejuk punya kawasan, you can easily get Q dot here. Okay. For example, I give you a situation here. If the question didn't give you T1, T2 and T3 here, instead it give you T infinity 1 and T infinity 2 and all other constant given to you. Can you find T2? Can you find T2? T1, T2 and T3 dia tak bagi, tapi disuruh cari T2. Can you find T2? Of course, you can find it. Okay, refer to this slide. If you want T2, there, as long as you have total heat rate through the wall and you ada R convection 1 and R wall 1, you can use basic formula of this. Find T2 and so on. If you need to find T3, you can use this formula. Basically, this is only derivation of big formula. If you understand the formula, you don't need to memorize all this formula. You just need to derive by your own understanding saja. Okay. Later saya akan tunjuk macam mana nak tahu kita nak derive depend on the question. Okay, kita tak ingatlah formula, kita lebih pada understanding the situation, then kita apply formulation depend on basic equation. Okay. Untuk thermal contact, sebab wall 1 dan wall 2 ni dia ada heat transfer berlaku, so dia mesti ada satu layer. Kalau layer dia itu tidak rapat, apa terjadi? Ni diceritakan. Kalau dia rapat, we call this ideal thermal contact. Dia betul-betul rapat lah ni, sangat licin dan dia cepat, tiada air gap ataupun tiada apa-apa layer di antaranya. So we call this ideal thermal contact. But actual situation, ni boleh lukis sajalah. Actual situation, it is true, actual apa yang berlaku kalau awak rapatkan two surface of material, there must be non-contact. Dia mesti ada air trap kat tengah-tengah tu. Macam ni lah. So, this is we call it as imperfect thermal contact. There must be a temperature drop between two metal. Okay, berapa licin pun you buat, dia akan mesti ada air trap. So you cannot get an actual ataupun ideal thermal contact. Ideal thermal contact ni hanya pada analisis saja, but in actual dia mesti ada air trap kat situ lah, where you boleh bayangkan lines ini adalah heat you transfer from left hand side to the right hand side. Kalau dia transfer to ada gap air di tengah-tengah dia, so dia akan berlaku convection lah, dia tak berlaku solid conduction. So bila berlaku convection di tengah-tengah tu, so dia punya transfer rate agak kurang lah berbanding yang dia full contact. Di sini full contact, full conduction. Okay. So you can read through here. When two such surfaces are pressed against each other, the peaks form good material contact, but the valleys from void filled with air. Kalau dia betul-betul ada contact yang cantik, dia akan form two contact lah, ada two conduction material. Tapi bila dia tak ada contact, dia mesti ada air in between. So these numerous air tu dia ada bermacam-macam saiz dan dia akan bertindak sebagai insulation. Insulation ni apa? Dia akan bertindak sebagai resistant lah, yang tak memudahkan heat to transfer dengan mudah, ataupun dia akan bagi insulate surface tu. Okay. Thus, the interface offers some resistance to heat transfer, and this resistance per unit interface area is called thermal resistance contact, RC. This is experimental setup lah kalau dia nak kaji thermal interface. Ni thermocouple yang lain-lain ni, dan ni first specimen test dan ni second specimen test. Dia nak kaji interface tu. So dia press apply load, press apply heat, dia tengok kat sini ada berapa heat transfer. So from numbers tu dia boleh tahulah interface tu dia akan varying the interface lah. Ada yang kasar, ada yang betul licin, ada yang sangat licin, dan dia takkan dapat ideal contact lah. So dia ada numbers dia. You can see this table here. Dekat contact tu you fill with air, so dia akan menjadi contact conduction ialah 3640 lah, the worst conduction lah. Kalau you isi di antara tu dengan helium, improve sedikit conduction tu, tapi bila you replace dia punya gap tu dengan sama ada air ataupun helium dengan hydrogen, conduction is much more better lah. It even further with silicon oil ataupun glycerin. Right, this is all the study of a thermal contact conduction. We not go even further with that, no problem. And we go with generalized thermal resistant network. What happened if your network it is in parallel? Dia ada parallel. For example, look at this figure. The temperature you apply dekat left hand side here, then the right hand side much more cooler, so the heat transfer through this will be like a parallel resistant network, macam parallel lah. So you can treat resistor tu as a parallel. Bila treat resistor as a parallel, you kena gunakan parallel network equation lah untuk resistance. So 1 divide by R total equal to 1 over R1 tambah 1 per R2. Kita nak R total tu, so you kena pusing-pusingkan dia untuk dapatkan R total. Dah belajar kan yang ni dekat electric and electronic, tak salah saya, electric and electronic subject. So you need to find R total first, then you can find heat transfer of that system. How about the combination of parallel and series? This is a parallel and series. You must treat it as a resistant network. Macam you buat circuit lah, circuit teori tu kan, macam you buat circuit teori. Kalau parallel you treat it as a parallel, kalau series you treat as series. Kalau combination of parallel and series, you treated their parallel and series. Okay. Next, example 3.1. Okay, enough talking. We do some example. Heat loss through a wall. Heat loss through a wall. Baca kat situ. Consider a 3 meter height, 3 meter tinggi, 5 meter wide and 0.3 meter thick of wall whose thermal conductivity is K equal to 0.9 watt meter K. K itu referring to Kelvin. Okay. On a certain day, the temperature of the inner and outer surface of the wall are measured to be 16 and 2 degrees Celsius respectively. Kemudian calculate the rate of heat loss on the wall. Okay, to solve this one, solve this one. Wait a second, nak cari poster. Let me draw pen there. Lagi kita nak pakai warna hitam. Saya boleh tulis lah. Given. So kalau you lihat saya punya cara penyelesaian calculation, saya always gunakan given di sini. Saya akan extract soalan tu lah. Kalau soalan tu selalunya dia tak bagi gambar pun. dia bagi wording macam ni lah, statement macam ni. So saya akan gunakan given. So saya akan, kalau dia tak ada bagi gambar, saya akan lukiskan dia. So given, we have 3 meter height, simply sketch 3 meter height, 3 meter, wide dia 5 dan thickness dia ialah 0.3. So temperature, the hottest part 16 degree, the cooler part is 2 degree Celsius. Fine, belum fine lagi. K given, K the wall 0.9 watt meter K. Okay, K is referring to Kelvin there. So the formula that evolved for this is basic equation, which is K times A, surface area, times T higher minus T lower, itu divided by L. Right, this is basic formula kan. You boleh terus simplify guna basic formula ni. Tapi kalau you nak gunakan resistance, you kena simplify using R equal to L divided by KA. So your R is actually L given berapa? L ialah 0.3. Kemudian K ialah 0.9. Dan area awak adalah 5 times 3 there. 3 here. 3. So your R total is, kalau you press you punya calculator, you will get 0.022 degree, sebab dia bagi K kat sini kan. So you K lah, K per watt. Ni unit up. K sama ada K per watt ataupun degree C per watt. It depends, sebab Kelvin ni unit temperature juga kan. 1 degree Celsius nak pergi Kelvin ditambahkan 217 kan. Sorry 273 Kelvin. Kalau you ada 100 degree Celsius nak tukar ke Kelvin ditambahkan 273, so you boleh dapat 373 degree, yang tak degree terus K, Kelvin. So in this case dia given you ialah Kelvin, so you need to convert degree C to Kelvin ni. So this is your R. How about the Q total? Q total equal to T1 tolak T2 bagi R. So you punya T1 16 tambah 273 tolak T2 minus T2. T2 you ialah 2 degree, 2 tambah 273 divide by 0.022. Since 273 tolak 273 dia benda yang constant, you boleh delete out dia macam tu saja. So 16 minus 2 tinggal 14. So 14 divide by 0.022, you can get Q rate awak ialah 6630 watt. So this is your final answer for example 1. Only conduction involved in this problem, hanya conduction saja. Sebab apa kita tak measure dia punya convection? Sebab dia tak bagi tahu kita berapa nilai H. Sebab convection yang berada di luar ni perlukan nilai H. Di luar ni perlukan nilai H. So kalau tak ada, kita tak boleh solve lah. Kita hanya disupply dengan nilai K. So kita akan solvekan conduction saja. Alright. Next question. Heat loss through a single plane loss through a single plane window. Ni single plane window. Sebab apa cakap single plane window? Sebab ada single ni lah. Dia, it could be double pane window. Double pane window ni window satu glass. Tengah-tengah dia ada air trap. Kemudian ada window lagi, glass lagi. Ni air. Ni glass. Ini double pane window. Yang ini yang kita buat ni, yang kita cuba selesaikan ni adalah single pane window. So bila single pane window, how to solve that? The easiest part is to sketch. To sketch a resistance here. Since we will only use thermal resistance concept, so you need to find resistance there. So the resistance equal to, ataupun R total equal to R convex. Kalau for this situation, R convex plus R conduction plus R convection. R convection tu berlaku kat sini lah, yang first punya. Kemudian R conduction yang second berlaku kat glass awak tu. Kemudian the third one is R convection, berada di luar ataupun di dalam, depend on situation. Okay, read here, dia cakap tinggi glass window tu ialah 0.8 meter high, lebar dia 1.5 meter wide, dan thickness dia 8 mm. Make sure you nampak kat sini dia tulis 8 mm. Unit tak sama, sini unit meter, sini unit meter, sini unit mm. Boleh you tambah macam tu saja kalau dia suruh minta tambah, tak boleh kan? Sama juga situation macam ni, ada unit tak sama, you immediately change dia. Okay, baca kemudian, calculate the steady rate of heat transfer rate through this glass window and the temperature of its inner surface for a day during which the room is maintained at 20 degrees Celsius. Saya tak tahu mana satu inner ni. Kalau inner dia outdoor ni, cakap dia kita tahu kat sini. Outdoor dia ialah, so sini outdoor, sini indoor. So dia suruh cari inner, T1 lah, suruh cari T1. So given H 0.8, Y 1.5, tulis unit, thickness L 8 mm, 8 darab 10 kuasa 3, tukar dia siap-siap. Kemudian conductivity given 0.78 watt meter K. Kemudian apa lagi dia bagi? H1 10 degree pula, watt meter square K, dan H2 40 watt meter square K. Then solve for Q dan T1. Okay, Q dan T1. So nak cari Q1 ataupun Q, you kena cari R total. How to find R total? We know that R convection di sini sama dengan 1/HE. Tambah untuk conduction di tengah-tengah gelas. Sini apa formula dia? L bagi KA. Dan another conduction is 1 HA. So ni H1, sini H2. So you solve for RT. Solve for RT. H1 di mana? Sini ada tulis. Ni H1, sini H2. A macam mana nak cari? A ialah height times width. L berapa? Ada kat sini. K berapa? K. Semua ada kat sini. Awak masukkan dalam kalkulator, awak dapat terus R total. Dia dapat terus R total. R total yang saya kira lebih kurang dapat 0.112 unit dia bagi K. So unit dia supposed to be K over watt lah. K over watt untuk R total. Then you apply a basic formula. Q equal to T highest, which is in our case is 20, minus T lowest divide by R total. 20 minus 10. R total 0.112. Ni Kelvin bukan kilo, okay? So the answer is dua enam tujuh 0.02 watt. Ini adalah Q keseluruhan. You baru dapat Q. Remember, you hanya baru dapat Q. And you tak dapat lagi T1. Macam mana dapat T1? Lihat kat sini, T1. So, from basic formula, you know that Q equal to T highest 20 tolak T1 di sini divide by R convection 1, bukan R total, bukan R conduction, bukan juga R convection 2, tapi R convection 1 sebab dia berlaku kat sini saja. So you nak dapatkan T1. Q pakai yang mana? Q yang you pakai yang tadi ni. Immediately you can get T1. You pusing sajalah kan. R darab Q, kemudian tambahkan dengan 20. Bukan tambahkan, ditolakkan dengan 20. So you pusing dia, you dapat T1 dalam negative answer, which is minus 2.16 degree C. Okay, degree C. So that is how you want to find the T1. Can you find T2? Easy, sama juga. Q equal to T2 minus 10 divide by R convection 2. Q ambil yang mana? Q ambil yang you kira tadi di sini. Sama. R convection dapat kat mana? Di sini. Yang you kira kat sini. Itu R convection you. Tambahkan darab dengan Q. Yang ini pergi bawah sana dapat nanti tu berapa. You can test. You can test your understanding dah. Right? Next, untuk last example. Last example dia kat tengah-tengah pula kat sini. Macam mana nak tulis? You boleh buat sendirilah. Saya tinggalkan untuk you example ni. If you tak kerti nak selesaikan dia, you boleh tengok dekat buku teks. Tengok macam mana dia selesaikan. Basically sama saja macam apa yang saya buat ni. Sama saja, cuma apa yang berlaku di sini ialah ada 1, 2, 3, 4, 5 resistan. So you kena kira lah. First convection, kemudian berlaku convection, berlaku lagi convection, kemudian berlaku conduction, berlaku lagi convection. So ada 3 kali convection berlaku dan 2 kali conduction. Sama saja guna thermal resistance. Okay. That's it today our lesson. Next week kita akan cover heat conduction in cylinders. heat conduction in cylinder. Still in steady and one dimensional, not 2, not 3, but one dimensional. Okay, hope that you take a lesson for today. We will continue on the next class. Thank you. Don't forget, we will have some quiz on wall heat transfer, wall plate. Yang ni cylindrical dia berbeza formula dia banding dengan plate. Okay, itu saja. Assalamualaikum warahmatullahi taala wabarakatuh.